Welcome back, everybody. Today, it's my great pleasure to introduce our speaker, Marian Mrozek. Marian obtained his PhD in 1982 from Jagiellonian University, where he studied under the supervision of Stanislaus Svezvi. He obtained his habilitation in mathematics in 1990 at Jagiellonian University, where he's now a professor. He's also a professor of computer science at National Louis University in Poland. His early research focused on graph theory and biological modeling and dynamical systems theory. Later, he became particularly interested in topological dynamics, where he did really foundational work on the Conley index theory for discrete and multivalued dynamical systems. In the early 90s, this work led to Marian and Pavel Pilarczyk and Konstantin Mashaikov giving the first proof, real rigorous proof of the existence of chaos in the Lorentz system. At the time, that was already a 30-year-old problem. In fact, the result was recognized by Encyclopedia Britannica as one of the four most important achievements in mathematics in 1995. He supervised 12 PhD students, including our good friends Daniel Wilczak and Piotr Gudzinski, and published more than 88 scientific papers. We're delighted that he's agreed to come and speak with us today about combinatorial and topological dynamics. Marian, the floor is yours.
Thank you for the invitation to this wonderful seminar and for the kind words in the introduction. Actually, it's really amazing to see how the field of computer-assisted proofs in dynamics grew over the last 30 years. And I really must admit that it's a very nice feeling to be still associated with computer-assisted proofs, despite the fact that I have no results in the field since the time mentioned by Jay, this chaos in the Lorentz system result. After completing this proof, I got interested in problems in computational topology, which got me involved for several years. But the last 7 or so years, I'm back in dynamics, but in this unusual flavor of dynamics, which I call combinatorial topological dynamics. I put here on the slide, because this is a quite huge project and I collaborate with several people on this project, but today I'll concentrate on the recent results obtained together with Thomas Warner and my colleague in Krakow, Romek Strzednicki, and also our students, Michał Lipiński and Thomas is, so Michał is my student and Thomas's student, Justin Thorpe. Okay, so the main motivation to study combinatorial topological dynamics, of course, the real main motivation is just because it's fun. But I think there are reasons to believe that this approach to topological dynamics may be useful in what I call sampled dynamics, sampled dynamical systems. A hint that it may make sense to do that approach to dynamics comes from two sources. One is Forman's combinatorial Morse theory, very successful translation of the very classical and complicated result to the very elementary, actually, counterpart in this combinatorial setting. And the other is the recently rapidly growing field of topological data analysis, which is oriented maybe not yet so much on dynamics, also in dynamics to some extent, but to trying to get understanding of topological spaces just from finite samples, from these clouds of points. So if this is possible, then it's natural to expect that maybe these topological tools may be also carried over to this combinatorial setting and combined somehow with the achievements of topological data analysis. Okay, so a few words about sampled dynamics. By a sample dynamical system, I mean a system which reveals itself only through a finite data set. It may come from observations, from experiments, but they may also come from evaluations, as it happens actually in every computer-assisted proof, because you can do only finite amount of computations based on finite amount of data. So in some sense, even there you can see a combinatorial dynamical system. But typically, these sample dynamical systems have source in time series from collected data, or in a cloud of vectors. So you can have a cloud of points, but at every point, if there is some movement in the phase space, you can maybe measure the direction of the movement, and this way you obtain this finite probe of the dynamical system in the form of a cloud of vectors. And of course, you can do the standard way of treating such dynamical systems. Since the classical theory of dynamical system is so deep and so well developed, then the natural thing to do is just to try to move things quickly into the setting of the classical dynamics. So you just try to approximate the data by a regular function, a polynomial, a rational function, whatever, what you find suitable, and then investigate the associated classical dynamical system. So for instance, out of this cloud of vectors, you just find let's say polynomial vector field which fits possibly well the data, and then you study this differential equation coming from the vector field. But there is a small catch in this approach, because you start with finite reality, the finite data set. Then, because of the availability of tools, you move to this continuous setting. But then typically you still have to discretize again, because as we all know, unfortunately, analytic tools are not very helpful apart from maybe a very small selected class of problems. So the possible alternative is just to try do the reverse. Instead of moving the problems to the continuous setting, just bring the continuous tools from the classical setting and somehow try to do everything immediately in this combinatorial setting. This actually happens also in a certain kind of computer-assisted proofs, the way we did it particularly in our old proof of the chaos in the Lorentz system. But probably this is what is still of interest if you try to get a kind of global, rough but still rigorous understanding of what's going on without going into plenty of numerical experiments, because actually many very fine, very sharp results obtained by means of computer-assisted proofs require a lot of work just to prepare the proof, just to set up the necessary tools before you can start the machinery and get the results. So sometimes you are lazy, you are happy with at least some rough understanding done automatically. Of course, this is still a far goal to do something like that. But the way you start this job is just you divide your space into some collection of finite cells, cellular decomposition, and then you pick up each cell, you make your rigorous enclosure of the value, and this way you arrive in something very combinatorial in its nature, this combinatorial multi-valued map or directed graph, because this is just the matter where do you come from. These are the same objects, just the languages are different because people come from different sources. Okay, so the outline of my talk is I want to spend some time first on these combinatorial topological spaces. Then I'll have a general look at combinatorial topological dynamics, but I want to concentrate on this special sort of combinatorial dynamics coming from combinatorial multivector fields, a generalization of Forman's vector field. because in this, so this is the setting which somehow corresponds to the classical case of a flow or semi-flow. But you can also look in a counterpart of a dynamical system with discrete time. Then I'll present the basics of the Conley theory in this setting, and I like to finish with formal ties between the classical and combinatorial dynamics. And this is where we recently realized that actually this may be helpful also to set up certain proofs which so far were not thought this way. So they were done, but using different tools. Okay, so these combinatorial spaces. So the first thing is you take just a classical topological space, think of a subset of a Euclidean space. In this example, just a square on the plane. Then I define a D cell to be a homeomorphic image of the closed unit ball in Euclidean space. So in this example, just this triangle. I use the circle notation to denote the associated open cell, so the image of the open ball. And then I define a cellular structure on this space X. Of course, it may not exist, but if it exists, it's of interest to us. So it's a finite family of cells such that if an open cell intersects in a non-empty way another cell, then actually the cell must be a subset of the other cell. So it must be its phase. This inclusion is used to define phase relation between cells. And X is the union of all open cells. So here in the right, you can see an example of a cellular structure on the square. It consists of, I think, 8 triangles, 9 vertices, and a number of edges. Here it's drawn so that you clearly see that this is a partition. They are disjoints, these open cells. This is an easy consequence of what we here assume, that the open cells must be disjoint. But typically I draw them just together like on the left-hand side. This let me define a class of sets in my ambient space, the subset of Euclidean space, which I call representable sets. So here is another example, planar disk with a cellular structure consisting of 4 vertices, 4 one cells, and 1 two cell being the interior of the disk. And then when I take an arbitrary collection of open cells and take its union, I use this absolute value notation because it's more convenient, it's shorter. This leads now from this combinatorial setting where I see, by the way, these black dots are just here to emphasize that sometimes, and actually in most cases, I will have this combinatorial look. So on one hand, these are cells in Rn, but on the other hand, I just want to treat them as points in this finite collection of cells. And this will let me draw, actually, use also the directed graph approach to represent maps. Okay, so support of such a collection is just the union of all the cells. So this way I obtain a map from this combinatorial setting to the classical space. And I say that a set is representable if it's in the image of this map. So it may be represented as a union of cells. Okay, so this is one thing. The other thing is that the cellular complex may be also considered as a poset. The phase relation gives you the structure of a partially ordered set because it's defined by inclusion. And we know that for posets, there is this Alexandrov topology, non-Hausdorff topology, consisting of upper sets. Upper sets are sets with the feature that if something is in the set, then everything above this is in the set. Sometimes you use the dual approach because it's here equivalent. So you can replace upper sets with down sets and vice versa. So why shall I mention this Alexandrov topology here? Because on one hand, it's easy to check that if you have a collection of cells and it's open in this Alexandrov topology, then its support, it happens if and only if its support is open in the Euclidean topology and vice versa. So in some sense, one could say you could just borrow the concepts of open and closed sets from the Euclidean place, and there should be no need to mention this Alexandrov topology. This is half of the truth, because yes, you can avoid mentioning this finite topology, but then it's difficult to explain why certain technicalities in this combinatorial dynamics are set up differently than in classical dynamics. Actually, this was a big block in my head, and maybe not only in my head, because I tried with Konstantin to do something like that 25 years ago, I think. At that time, we did not think to do this in right topology, and somehow this block caused that, so something had to switch in my head so I could see things properly. Fortunately, on the level of algebraic invariants, these topologies are the same. So they are very different as topologies, but homotopy and homology groups of the cellular structure and the original Euclidean space are the same because of the McCord's theorem. Okay, so actually this Alexandrov correspondence gives you more because it's functorial. One can show that there is a functorial correspondence between the category of finite preorders, so you don't need even an order, it's enough to have a preorder, and the category of finite topological spaces. And this gives you this dictionary, which lets you translate concepts from finite topology to orders and vice versa. This is very useful in algorithmic terms, because if you have to solve something in your topological language, you just look into the translation into the POSIT, and in many cases, the solution is already there. The necessary algorithms are already directly not only available, but implemented. Just take and use them. For us, what is important is this concept of locally closed set, a concept rarely used by topologists, but you can find the definition at least in some textbooks. So here is the definition: a subset, it doesn't matter now what is the topological space, it may be Hausdorff or non-Hausdorff. A subset is locally closed if its mouth, which is the closure of its set minus the set itself, is closed. And this is equivalent in the POSIT language to being convex. A subset of a POSIT is convex if it has the feature that if 2 points are in the subset, then everything in between the two elements is also in the subset. So this is an example of a set which is not locally closed. And the mouth here is marked in brown. It's clearly not closed. And here is an example of locally closed sets. The locally closed sets somehow replace the role of compact sets